Okay, I was saying that if x and I, xj are far apart, then you're penalizing 0. And if they are close, then wij is large, making y and yj close to each other. So that we want to take care of this when they are close. We want to penalize it. If yi minus yj gets big. So if xi and xj are close, then this wij is large, and we can, it's very similar, I mean the idea is very similar to spectral clustering, even the solution, and it becomes, if you just work on that, it becomes minimization of trace of y transpose Ly. Again, in order to make it non-trivial, we subject it to y transpose y is equal to I, where y is P by N matrix, and X is D by N matrix. And this is, so the solutions are eigenvectors of L, where L is your diagonal minus weight. So this is the Laplace. So the eigenvectors of Laplace is a solution to a Laplacian eigenmap. Just very similar to spectral clustering. K-means is clustering an original space X, but spectral clustering is clustering on space Y. And now I want to talk about another dimension reduction method, which is called stochastic neighbor embedding. It is an article in 2002 by Sam Royce. Fortunately, he died very soon. And Jeffrey Hinton in Toronto, I think, the father of deep learning. And so for each object I and each potential neighbor j, we define Pij, we interpret it as I would love to pick j as its neighbor if Pij is equal to e to the dij squared, sum of these exponentials, dik, but k is not equal to I. And dij is the usual distance over 2 sigma I2, which is a binary search. This one is a binary search that makes the entropy of distribution or over neighbors equal to log of k. And so k is called effective. K is called effective number of local neighbors, this k, and it is also called perplexity. In low dimension space, fixed variance is set to 1/2 in this article, and we have another discrete probability, which is equal to this time in the transform space. Again, k is not I exponential minus yi minus yk squared. So we want to match these two distributions. You know, the similarity of two distributions is well explained in different areas in machine learning, such as, for example, somebody use Wasserstein distance, others use Bregman distance. Of course, I've noticed that Kullback-Leibler divergence is a special case of Bregman divergence. And so the general case, even Bregman divergence can be generalized to something else that I don't remember, but we can match these distributions, P and Q. So we can write it as we want to minimize the Kullback-Leibler divergence between Pi and Qi over I. And this is exactly Pij log of Pij over Qij. And so stochastic neighbor embedding is improved over local linear embedding. Even it outperforms self-organizing maps. So we have defined C, this one, and then take derivative with respect to yi. It becomes 2j yi minus yj Pij minus Qij plus Pji minus Qji. And this is the idea of stochastic neighbor embedding.